Hello everyone. So this is subsequent to what we have covered so far on Big O Basics. Uh, so let me go through what we have covered so far. So just before we start it, so I would like to mention here about the references which I have taken to create this series on Big O notations. So it's the technical blogs on internet I have gone through in the last few months to create this useful content, as well as there is a famous book on computer science like cracking the coding interview, sixth edition. So this is also I have basically uh, read in the past, and as well I have used some generative AI tools like ChatGPT, Gemini, and Claude to understand big O notations, and as well to first clarify my own queries. And that's how I have created this really useful concept in a more friendly manner. So with that, let's keep going. So far, this is the part three, and we have so far covered part one and part two on big O notations. So in part one, we basically started with what the big O notation is and where it is used, and then some of the terminologies used in big O notations like asymptotic runtime or runtime of an algorithm, or what is an algorithm, and what is big O in the sense that it is a metric or a language used to judge efficiency of a computer program. Then we looked at time complexity and some part to space complexity, in the sense that there are some common patterns on time complexity like order of n, order of 1, and then few others like order of log n and things like that. And then we also noticed that there is no fixed list of possible runtimes. It depends the logic of the code. And then to determine the complexity or to represent how the runtime is in terms of input. So there are three different techniques. One is big O, big omega, and big theta. So I would say there are three aspects to think of when we want to judge the efficiency of an algorithm. So big O refers to or describes the upper bound on the runtime. Then big omega describes the lower bound on the runtime. And finally, we have big theta, which is the tightest bound on the runtime. We also made a note that whenever we are determining or analyzing the efficiency or runtime of an algorithm, then we will always look for tightest runtime, tightest bound on the runtime, right? So one thing I would like to mention here is like anytime uh, during the se- during the series, if you are listening to, if you have any questions on anything, just drop the comment and I will try my best to answer query. Yeah. With that, in part two, what we covered is best case, worst case, and expected case scenarios. We noticed that if the data is like we know there can be a random kind of data. So based on the data set or based on the input to a function, for example, so we can have best case scenario, worst case scenario, and expected case scenarios. And as well, we also basically looked in as an example wherein we were trying to find a number in an given array, wherein the best case would be that we just see the number is there on the first index. That is the best case scenario. And the worst case is we do not find the number at all. That is the worst case scenario. And average case is when the number is located in the middle of the array. Okay. So this is what we have covered so far. In today's part 3, we will be covering a few more on the big O part. So let's talk about the space complexity, right? So space complexity is a parallel concept to time complexity. So for example, if we have a Java function, like if I take the Java function, this one. So here in this function, one part is like how this function is how this function will perform based on the size of the input, right? So that is like how much time it is going to take. And then basically the second part is how much memory it can take, right? So that is what space complexity is all about. So how much space my Java program or Java function is taking when it is running. So that is the space complexity. So space complexity is a parallel concept to time complexity. It's not the only thing, like time is not the only thing that matters in an algorithm. We might also care about amount of the memory or space required by an algorithm. So both are really important if we look at all the aspects of a algorithm, space and time. So just to start with some examples. So for example, if in a algorithm or if in a Java function, let's say we are creating size, we are creating an array of size n. So it means that it is going to take order of n space, right? Likewise, if in our Java function, we have a two-dimensional array defined of size n is to n, and we are working on this, we are filling it up, then this there the complexity will be, space complexity will be order of n square, right? So that is what space complexity is all about. So now you will see some recursive calls, right? So recursive calls is like, for example, we have this sum function, right? In this sum function, it takes n integer and returns int, right? So now what we are doing here is, so for example, we want to determine its space complexity. So it means like how much space this will take based on the input. So what we will notice is what we are doing in this function. So we are saying that if n is less equal to 0, return 0. Otherwise, return n plus sum of n minus 1. So for example, if I started with 5, then what we are doing is we are saying the actual call will be 5, return 5 plus, then it will go to sum 4, then it will go to sum 3. So basically sum 2, sum 1 and sum 0. So basically every time we are calling the same function with one value less. So 5 plus sum of 5 plus sum of 4 plus sum of 3. plus sum of 2 plus sum of 1 plus sum of 0, like that, right? And then when it determines sum of 0, then it will come back to sum of 1, right? So it's a recursive call. So it means that to determine sum of 5, it has to go till sum of 0, and from there it will come back, right? So if I basically draw it over here, so my n is 5, right? And then it has to do calculate sum of 5, right? So it will first go to sum of 4, then it will go to sum of 3, then it will go to sum of 2, then it will go to sum of 1, then it will go to sum of 0. And at this point, it will not go further, because at this point we are returning 0. So then first it was doing like this, then it will come back. So it will be here. So it will be returning 0. And then here will be doing 1 plus 0. What is 1 plus 0? It's 1. Then it will go here, right? So 2 plus 1, which will be 3. And like that, it, it will get resolved step by step, right? So what we are doing here is to determine 5, sum of 5, we have to keep going down till 0, and we have to hold everything in memory. And how many times we have to hold it in memory? Everything, like each step, 5 to 4 to 3 to 1 to 0, like that. So it will be order of n. So that is what the space complexity is all about. So we are determining how much space this program will take when this will run for a given value of n. And now if I talk about the, let's say, time complexity of the same function. So time complexity, what will happen? So basically if n is 5, then I have to know sum of 5, I need to know sum of 4, like sum of 3, sum of 2, sum of 1, sum of 0, like that. Then only, so then only we will know sum of 5. So how many steps we are doing? We are doing n steps. So therefore, the runtime is going to be order of n, right? Because we are doing n steps to determine sum of n. Now, let's say we have another example. This is the one, right? So in this example, what we are doing is pair sum sequence and then this. So here, let's say, so basically every time you have to find the time or space complexity of a given program. So you need to first analyze what we are doing step by step. So I'm going through this one in detail. So let's say it's n, right? Then we have a variable sum. So if I take like this, so this is my sum. Initially it's 0. So in memory, we will have a variable sum, right? And then we have a for loop. So in this for loop, what we are doing is we have I running from 0 to n minus 1, right? And then, so basically I will run from 0 to n minus 1, almost like 0 to n, right? So it will run n times. Whatever is my n, it will run n times this loop. And what we are doing in this loop is we are calling we are calling pair sum method where we are passing. So I will be like initially 0, then it will be 1, right? It will be 2, like that, and it will move on to n minus 1, right? So then, so far, in terms of in terms of space complexity, let's first talk about space complexity, right? So in space complexity, we have a variable. When this program will run, so we have a sum variable with value, initial value 0, and then we have a I variable, right? I variable whose value will change from 0 till n minus 1. So when I is 0, then we are calling this method pair sum, and we are passing 0 and 1, right? So once we pass it, so it will instantly call a function, and then function will immediately return, right? So as soon as it will return, we will add its value to here. So now sum will be 1, correct? Then what will happen? So this is now resolved. Everything is resolved now. We do not have anything in memory. So we wanted to determine, let's say n was my 5. So what we are doing is we have covered 0. Everything is resolved, right? It has returned from Pearson method. Now I go to 1. So likewise, we do the same thing 1 and its next element 2. So it will be called to this function, right? And this function will return sum of this. 1 plus 2 is 3. So now we have 3, and then whatever value we have on sum, it will be updated from 1 to 1 plus 3. So what is 1 plus 3? 1 plus 3 is going to be 4, correct? So now in the sum we have this. So what we are doing here is now 1 is resolved. There is nothing in memory at this time. Similarly, it will be for 2. It will be for 3. So every time we are on a particular index, then we are determining its sum of this index and its next index. And then we are updating the sum, this sum. So ideally in memory, we are not keeping everything on hold to determine the value of n. It's just a couple of variables. So it's like space complexity is constant. It doesn't depend on n. So to determine this pair sum sequence for n is 5, it's not that we have to hold it, we have to hold something for n is equal to 4, then n is equal to 3. It's just that we are iterating through each index starting from 0 till 4, and for each we are updating the sum. So that's why its space complexity is constant, order of 1, but its time complexity is order of n, because to determine pair sum sequence for 5, we have to determine, basically we have to do each step. So for 1, for 2, for 0, for 1, for 2, for 3 till 4, right? So so it depends on the input. So if input is big, large, then this will change accordingly, the time complexity. So it is directly proportional to the n. So that's why the time complexity is order of n in this case, and space complexity is order of 1. Okay. The other part is, so always remember, in whenever you see a question on time and space complexity, we can drop the constants. So for example, if we take this method, right, print items twice. So here we are taking an array, and then we are first printing out each element in this array, and then in the same function, once we finish this iteration, this first for loop, then we again have a second for loop on the same, right? So although in this case it's just order of n, and it's again order of n, right? So it is order of 2n, right? But it's just that we can drop the constant, it is still order of n. Okay, so we can always drop the constants. In this case, we are dropping the multiplier thing. I will take one more example. Uh, yeah, so in this example, if you see here, it's just to correlate these two programs. So in the first one, we are going through an array, iterating through it and doing two steps, right? And in the second one, we still have, so in this case, whatever we are doing, uh, so in this case, it's order of n, right? Because we are iterating through each element of the array, and then internally we are doing some constant stuff. In this case, we are iterating through array here in the first for loop, and then similarly in the second for loop. So here we are doing it order of 2n, but then we will drop the constant, so it will again be order of n. Okay. Then another example is if an algorithm only processes half of the data. So for example, in this case, what we are doing is, as I said earlier, so whenever we want to determine the complexity, time complexity, for example, so start analyzing what we are doing in the function. So we are taking array as the input, then we are determining its how much half, so number of elements divided by 2, right? And then so in roughly, if my size is 50, then I'm going till 25. If my size is 100, so my half length will be 50, like that, right? And then I am going till half and printing the value. So essentially, if I have 50 elements in original array, then I am just going till 25, half of it. But so ideally, technically speaking, the complexity of this is order of n by 2. But then we can drop the constants and still it will be order of n. Okay. Likewise, another example is, so we have this function which takes again an array. Here we print this each element of the array in first step. So how much is the time complexity? Order of n. Then what we are doing is, here we are printing something, so order of 1, right? Here we are printing something, so order of 1. Here we are printing something, so order of 1. But overall, if we look at it, right, think about the things we discussed earlier, big O, big omega, and big theta, where big O represents the upper bound on the runtime, big omega represents the lower bound on the runtime, and big theta is the tightest bound on the runtime. And we also said like we should always focus on the tightest bound. So in this case, I am doing something as many number of times as is the elements in my numbers array. So here the complexity is going to be order of n, because that is the tightest bound. This will finish very quickly, this step. This will finish very quickly. This will finish very quickly. Both all are the printout statements. Very quick. But this thing will keep running until we finish going through all the numbers in this array. So in terms of dropping the constants, so ideally it's order of n plus order of 3, right? Order of n plus 3. This is what we said. But we can basically drop this constant thing and it will be order of n. Okay. Likewise, drop non-dominant terms while determining complexity. So what does it mean is that if we have a complexity something like this, so we know my tightest bound runtime, my tightest bound on the runtime is this. So this this time is going to be uh, so we can basically drop this. So still the complexity will be this. Likewise, in this case, order of n plus log n, it the time complexity will actually be order of n. And in this case, the time complexity will be order of 2 to the power n, because this is the dominant term and this is the non-dominant term. As you have seen previously as well, when we were talking about drop the constants thing, so here we were first taking order of n based on the array iteration, but then the other steps we were doing in constant time. So the dominant term is order of n. Dominant term is order of n, right? So that's it so far. I know it is becoming more and more complex, but if we learn it in different parts, then I think it will be easy to understand the uh, complex things as well easily. Okay. So overall, what we have covered so far is, let me just quickly go through. Oh, so what the big O is, right? Then time complexity, most commonly used time complexities. Then big O, big omega, big theta. Then best case, worst case, and expected case. Then space complexity in general, what it is. Then space complexity in recursive calls. Then we said that we can drop the constants while determining complexity. And then we can drop the non-dominant terms while determining complexity. That's it for today. Thank you.